In this video, we're going to talk about force diagrams. These are diagrams that show all of the forces acting on an object. They show the force's direction and their magnitude. It's just a simplification of a picture showing only the forces that are acting on a single object. So we look at this book on the table, we're going to be talking about the book. Okay, so we just want to talk about the book. So what forces are acting on the book? Well, there's gravity, okay, and there's what we call a normal force acting up. So what we're going to do is turn that into a diagram. You start by making the object a single dot in the middle, and then you'll see that we've drawn an arrow for the force of gravity and an arrow for the normal force. Okay, and we're going to talk a little bit more about what these descriptions mean and why these two forces are the same size. So the steps for drawing a force diagram: first, identify the object you're going to draw and go ahead and circle it, and then identify all the forces acting directly on the object, okay, and identify what objects are exerting those forces. With the exception of gravity and magnetic forces, the two objects will generally be touching each other. Okay, you'll start by drawing an XY axis and placing a dot at the origin. The object is just going to be represented by that dot. And then we're going to draw a vector, or an arrow, to represent each force. And the way we're going to label that force is the force type, on, and by. So for instance, there was a force of gravity acting on that book. So I would call it the force of gravity acting on the book by the earth. Okay? If the acceleration is 0, then the net force is also going to be 0, and this is going to have implications about how we draw our arrows. If the object is accelerating, then we're going to have a net force that's not 0, and that also is going to affect how we draw our diagrams. There's a whole bunch of different forces that we're going to talk about. Okay, so we've already started to talk a little bit about the force of gravity. Okay, so force of gravity on an object, always by the earth. A normal force always acts perpendicular. Okay, so for instance, we had that table and a book. The normal force was acting perpendicular to the surface of the object. So that's just normal force on the object by whatever surface is touching it. Force of tension, okay, or just Ft, is going to be on the object through, say, a rope or a string or a chain. So this is when you're hanging something by a rope or something. We call that force a force of tension. Friction and air resistance. So the force of friction is going to be on the object by the surface. Okay, or if you're talking about air resistance, okay, it'll be on the object by the air. Same idea, really. Now, if the object is moving to the right, the force of friction acts in the opposite direction. Okay, friction and air resistance cause things to slow down. A magnetic force, okay, again, is always on your object. Notice that we're always talking about a force on the object. In this case, it would be by a magnet. Okay. A buoyant force is kind of like when you have a cork floating in water. Okay, so this is your buoyant force on your cork by the water. Lift has to do with a plane. Okay, so this is going to be lift, say, on a plane or a helicopter or something like that by the air. Okay, helps move them up into the air. Thrust is a little confusing, but this is a force of thrust, if I can spell thrust. on the plane by the exhaust gases. Okay, so what happens with a plane, I'm a bad drawer, so there's my plane, don't make fun of me. It's going to expel gases, okay, and the plane exerts a force on those gases, therefore the gases exert a force on the plane, and the force exerted by the exhaust gases on the plane is called thrust, okay? So what we're going to do now is just look at a whole bunch of examples, okay? So you've already seen this, but I'm going to start by circling the object I'm talking about, okay, drawing my dot and identifying my forces. So I've got gravity, and I've got a normal force. Okay. This book is at rest, therefore my acceleration equals zero. Therefore my net force has to equal 0. Because if there was a net force, it would be accelerating. So the force of gravity, I'm going to draw that straight down. F(g) on book by Earth. Okay, and since the net force is 0, the arrow I draw up has to be the same size. This normal force on the book, remember it's always on the same object, by the table. Okay, and then probably your teacher's going to want you to note when forces are the same or congruent. Okay, so we make little marks to say these two forces are the same. So note the force up and the force down are equal in magnitude, so when we add those vectors, we get a net force of 0. And that's why the book is sitting there. How about an egg falling from a nest? Okay, so this is going to be speeding up, right? It's going to get faster as it falls. So the acceleration is not 0, so we are going to have some sort of a net force. Okay, well, what forces are acting on this egg? Well, let's see, we've got gravity, and I think we probably have a little bit of air resistance, right? So, draw my object, I draw my gravity, force of gravity on egg by Earth. Now, how big should the air resistance be? Well, it's going to have to be smaller because we're going to end up with a net force going down because our egg is speeding up. So I'm going to draw a smaller arrow, okay, sort of force air resistance on the egg by the air. Okay, so there's your net force is going down. How about a bobsled sliding across the ice at constant velocity? So we're saying that the acceleration is 0, so the net force is 0. Okay, so I've got gravity. I've got a normal force. Now, if it's at constant velocity, am I going to include friction? Well, let's look at our force diagram and see if friction is being ignored here. So I've got my bobsled. I've got my gravity. Okay, force of gravity on the sled by the Earth. Got a normal force. F normal on the sled by the ice. Now, if I include friction, what's the force moving to the right that's canceling that out? So it must be that friction is not involved here, okay? Because if I tried to draw a force here, I'd have a net force in that direction, because there is no force acting to the right. There's nothing pushing the bobsled forward anymore, okay? So these are not there. And there's your force diagram. We're going to push a box across the floor. So we're talking about the box. The man is pushing at perpendicular, so this is going to be a normal force. Okay. Gravity is acting down. And there's also a normal force being exerted by the floor. Okay. So it looks like we've got a few different forces here. What do you think? Should there be friction too? I think there's probably a little bit of friction here, right? Let's add some friction. Okay, so I take my box and draw my gravity. Force of gravity on the box by the earth. Normal force on the box by the floor. Okay. I've got another normal force here on the box by the man. And I've got some friction. Okay, notice I'm going to draw it pretty small. Box by the floor, because the acceleration is not equal to 0. All right, it's accelerating in this direction, so we have an F net moving to the right. Okay, so these two forces are congruent, but the force of friction and this normal force are not the same. Okay, the one is bigger, so we end up with a net force to the right. How about a Hotchkiss student who's got a backpack on his shoulder? Okay, so it looks like we've got gravity, and then some force holding it up that it's a strap, so we'll go ahead and call that tension. So we draw our backpack, right? And you got your force of gravity on the backpack by the earth. And you got the force of tension on the backpack by the strap. Okay, and then we should note that these two things are congruent, right? It's just suspended there, so our acceleration is 0, so our net force is 0, right? We're just talking about this backpack. Okay, last one. I've got a car coasting to the right and slowing down. So the acceleration is not equal to 0, okay? It's asking us to neglect air resistance, all right? So let's see, we've got gravity. We've got a normal force. And we got some friction. Okay, so I've got my car, right? Got my force of gravity on the car by the earth. I've got a normal force, the same size, okay, on the car by the road. And I've got some friction, so the force of friction on the car by the road. So our F net is to the left, which makes sense, right? My car is moving to the right, but it's slowing down, so the net force must be acting against that. So these are some examples of some pretty simple force diagram. In the next video, we'll look at what happens when they have components.